Hi, this is Professor Fernandez, and we are working on class notes F in lesson 5. So in this class notes, I was hoping to prove this theorem up here, theorem 5.3.1. And to put that in context, let me scroll up very quickly and remind you of where we were. In the previous video, we had just seen how to apply how to solve the free vibrations case. So we were talking about this ODE here, and we had just solved that, and what we had obtained was this solution down here in blue. And this told us a little bit of information about what the mass on the spring does as it oscillates in the free vibration case. I had mentioned in that video that the omega sub zero here had come up as sort of an abstract out of the blue when we introduced it, but now we see that it is the angular frequency of the motion. The thing is that it's a little hard to see that from this expression, because this expression is a linear combination of two sine and cosine functions. So what's really going on in this theorem is that it's trying to get this linear combination and collapse it into just one cosine function to make the interpretation easier. And then the second thing that's going on in the theorem is that, remember, C1 and C2 for us, usually we find that by applying the initial conditions. So in this theorem, the C1 and C2 actually combine to make the amplitude of this cosine function. And then delta becomes like a phase shift, which we find using this, this formula. All right, so I wanted to talk through the proof of the theorem. I've written, typed out the steps down here. So I'm going to do this proof in what I'm going to call a reverse proof. So I'm actually going to start with what we want to prove and end up with where we want it to start. And then the proof, the actual proof, would be done in the reverse order. I'm doing that because if I do the proof in the order it should be done in, you'll see in a minute I'll have to introduce expressions for C1 and C2 that will seem like they come out of nowhere. And doing the proof in this reverse proof direction makes a little more sense. So first thing I'll remind you of is this trigonometric identity. So we are going to employ that up here. And first thing we'll do is we'll say, okay, so I have a cosine of a difference of two things, this omega naught t term and this delta term. So my x is omega naught t and my y is delta. So that's going to be omega naught t and that's going to be omega naught t. That explains these two terms. And then this is going to be delta and this is going to be delta. That explains this and this term. Great. So again, I'm doing the reverse proof. So I'm expanding this function and with using this trig identity. So I get down to over here. Sounds good. And then this is where I said the substitution, now it looks very natural. It doesn't look like it comes out of nowhere. So what I'm going to do is I'm going to say, okay, let's call this C1 and let's call this C2. So a few questions you might have here, right? How is this possible? How does this work out? Later on down the road, right, you might, if you want to go backwards, worry that is this substitution general enough? That is, if I know C1 and C2 up here from the original expression of y of t, can I always write C1 and C2 in these forms? And the answer is yes, because this, in the way that we're using it, is basically a version of polar coordinates. So let me just, review that very quickly. So suppose this is a C1 axis and the C2 axis, thinking of that as x and y. C1 comma C2, I can think of this as a point in the plane. This is what we're used to as Cartesian coordinates, right? You go this many units, C1 units to the right, then you go this many units, C2 units to upward, and that gives you the point C1 and C2. But there's another way to get to the same point. You can view it as I am going to go this many units out from the origin. I'm still going to call that C1. And then I'm going to go up a certain angle, delta, until I get to this point here, right? So that is exactly, you get to the exactly same point. And if you work out what's going on here, we take out this triangle here. Let me make it a little bigger and make it easier to see. take out this right triangle here. This side length down here is length C1, this is length C2, and this angle is delta. So what happens here? So if I write out cosine of delta, that equals the adjacent side, which is C1, divided by the hypotenuse. Let's call the hypotenuse A. And what would A be? A would be the square root of C1 squared plus C2 squared. Right? So if I solve this equation for C1, I get exactly this. C1 equals A cosine of delta, where A is square root of C1 squared plus C2 squared. Okay? And then if I were to go back up here and do the same thing, but look at the triangle from, instead of cosine, the sine of delta. Sine of delta is the opposite side over the hypotenuse. And then I solve this for C2, and that gives me this equation. And again, A again is the square root of C1 squared plus C2 squared, which I have there. So all of this is to convince you that really, if I have a C1 value and a C2 value, which those come from the initial conditions of the ODE, I can express them in this form. And all I'm doing in the background over here is changing to polar coordinates, where A is like the R value in polar coordinates, and delta is like the theta value if you studied polar coordinates before. All right, so I'm going to erase all that, and then I'm going to, or at least this part, and then I'm going to finish our derivation. So that gets us down to here. So we were here. This becomes C1. Okay. This becomes C2. Okay. And I'll scroll up a little bit and mention that that gets us in the reverse proof from here to here. So in fact, these two expressions are equivalent. We've already talked about A being the square root of C1 plus C2 squared. Let's now talk about this little piece. So if I go back up here, then I can say C2 over C1. C2 is A sine delta. And I'm going to divide that by C1, which is A cosine delta. I'm going to assume that the A is not 0, right? The only way that the A is 0 is if C1 and C2 are both 0. And then that would make the function y 0. That is certainly a solution of every homogeneous solved, but it is not generally the case. And if that is the case, we don't need all this fanciness with characteristic equations and everything we have been studying. Okay, so then sine of delta over cosine delta, that is tangent of delta. So tangent of delta is C2 over C1. That gives us that relationship. And going back up to the proof, if I want to find delta, the actual number that goes here, then I would take the arctangent of C2 over C1, which is the same as the inverse tangent. Okay, so I'm going to erase all of this so we can sort of stand back and talk about how the, quote, real proof would go. So if I were to do this in not reverse form, now that you see where things come from, I would start here, number 1, and then I would introduce this decomposition for the C's. And again, that is basically what is over here, writing the C's in terms of their polar coordinate forms. Okay, so with this decomposition of the C's, then I would substitute the C1 into here to get that term, the C2 into here to get that term. And then from here, I'm going to go here by using this trig identity, going from this side to that side, right? And then that gets me to this collapsed form. And then I would, so that's this substitution was the third part here, and then this collapsing was the fourth part. And then, I would finish up by noting that my original substitution, in my original substitution, this was the relationship between the C's and the A's, and this was the relationship between the C's and the deltas. Okay. All right, so I'm just going to erase all of this so that next time that we need to come back to this in a future video, it's not so crazily scribbled everywhere. But I'll leave the polar coordinate stuff. That might be useful later on. Okay, so that's it for this theorem and for the video.